Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside and let's look at function inverses. Now you're on the integrated math 3 track where I've been doing some things where I've been transforming quadratic functions and cubic functions using the a, b, h, and k material. We've looked at odd and even functions as well, where we've reflected across the y-axis or the origin. And we're going to be doing a reflection of sorts here, and not like on purpose on our own. There's a way that we can do it. You might have done it in the past as well with objects. We're going to be reflecting across a diagonal line, though, using what are called inverses. And what inverses are, just to give it in a nutshell, it's where your x and y values of some function trade places. The x's become the y's and the y's become the x's. And we're going to be creating inverses of functions, because they're not all functions. I'll show you what I mean in a second. We're going to be creating inverses of functions algebraically. We'll represent a couple of them on the graph, and we're going to test whether two functions are inverses of each other, all in 10 questions on a worksheet that I kind of just created here. So we're going to take a look at it right here, right now. And before I do some of the problems, let me kind of give you the example or the representation of what the heck a inverse is in and of itself. So there's this, there's this diagonal line right here. This line has a slope of 1, rise 1, run 1, and it has a y-intercept of 0. This is the equation of the line called y equals x. If you take any object, whether it's a graph or a shape or whatever, and you reflect across this line, like I say with my kids, I do something like choose the letter F right here. If I take this letter F right here, and I reflect it across this line, there's a specific appearance that it takes on. And this appearance would just so happen to take on something like, it would look like this right here. This is what reflecting across the line y equals x would look like in this case. And if you tilt your head the correct way, I guess I got to do it this way for you. If you tilt your head the correct way, you'll see what I mean as far as that being a mirror image of that F going across there. But what you're actually truly seeing are certain points reflecting across that line in such a way that the X's inherit the Y's and the Y's inherit the X's. Like this point right here, the middle of the F, that's 3, 0. Well, this point up here is 0, 3. And that's what happens when you have something reflect across that line. Now, when something reflects across that line, it is considered to be its inverse. The inverse is the swappage of the x's and the y's. The x's inherit the y's inherit the x's. There's a point up here and a point up here that are inverses of each other as well. 5, 2, 2, 5, things like that. So anyway, we're not going to do it with the letter F. We'll do it with actual graphs themselves. We can actually draw the graph, and without even intentionally drawing by reflecting across this inverse, we can create the inverse equation, and we can actually draw the inverse of that function on there, and you'll see that it reflects across in this way. So the first two ones, we're going to graph and test that together. So how do we create a graph so that the x's and the y's swap with each other? Well, it's actually really straightforward. See, g of x here in this problem, g of x represents y. So see this y equals 3x minus 6? I can create an inverse of this, and inverse meaning swapping x and y, by swapping x and y. I can actually swap x and y right here, and I can take where y is, I'm going to put in place of x. Where x is, I can put in place of y. This equation right here, x equals 3y minus 6, this is the inverse of this function right here. Now, how do you graph this? I would try and get y by itself to graph it, because we're really good at that whole input-output thing, slope-intercept form. There's some tableless graphing that we know how to do. So what I'm going to do is I swapped x and y. Now let's get y all by itself again in this equation. This equation already is an inverse, but let's get it by itself so we know how to graph that in the best way of plug in x, get out y, or use the slope-intercept form. So if I add 6 to both sides, I'm going to get x plus 6 equals 3y. If I divide both sides by 3, then I'll get y equals x plus 6 all over 3. But let's split the 3 up, right? Let's create a mx plus b. 6 over 3 would be 2, right? So x over 3 is 1/3 x. 6 over 3 is 2, so y equals 1/3 x plus 2. And that is the inverse here. Now, we want to represent this in such a way that we note that it is its inverse. Inverse notation, if that's what you call it, function inverse notation, is if this is g of x, the inverse appearance would be, it looks like this. It's not to the negative first power. That's just a way of denoting inverse of a function. So this is the inverse of g. It looks like it says g to the negative first power. It's not. It's the way you say inverse of g. We do the same thing for trig functions, for inverse sine and inverse cosine and things like that. So the original looks like this. Now, I purposefully did put a y there to begin with, this one right here. I don't like putting a g of x on this side and getting g of x, but it's iffy to me. I like saying the y. It's not required. But remember, once you put it here, it's no longer g of x. Now it's inverse of g right there. So anyway, let's graph these two separately. Let's graph them separately, and let's see how they appear in comparison to reflecting across that line. Let's see if it makes sense that all the x's inherited y's and the y's inherited x's. So I'll put one in green, one in purple, and well, you know what? Let's put them as the same color. Let's see if the same color, different colors for now. I'll black and white later. I don't plan this stuff out clearly. Okay, so let's do the first one. 3x minus 6. That means a y-intercept of negative 6 right here, and a slope of 3 means up 3 over 1. Up 3 over 1, up 3 over 1, like this, etc. And then you have a line that goes like that. Okay, so that's this guy right here, right here. So there's that g of x. That's the original function. What does the function's inverse look like? Well, let's graph it. So this one here, 1/3 x plus 2. So a y-intercept of 2, rise 1, run 3. Rise 1, run 3, and let me go the other way as well. Fall 1, run 3 to the left, like so. And let's graph that line as well. So that one, let's see if this makes sense as far as reflecting across this line and such. Okay, so here are our two lines. Now, if you tilt your head the correct way, can you notice that one is a mirror image of the other? That at any one point on one of them, like this point here, 1 comma negative 3, that you have a reflective point over here, negative 3 comma 1, where the x and the y swapped. I mean, it makes sense. We only, swapped x and y here, right? We only did that, so why shouldn't they swap on the graphs themselves? Well, they should, and they do. And then, what's going to happen is they also do intersect on the reflecting line somewhere. If they go across it, then you're going to see them intersect at the same spot, because that's a point where x and y are the same, 3 comma 3. Right, so that that's something that's going to occur as well when it comes to it. So graphing this kind of confirms the idea that these two functions are indeed inverses of each other. There's a way to test that we're going to do at the end. There's a way to test to see that if you were given these functions, whether they're inverses of each other without swapping. It's kind of a weird way of going about it, but you'll see it. But anyway, so there's the graph, there's the confirmation there, and yeah, we're good. If I did this all in black and white, so you can see it in the way that you're going to possibly be drawing, it's going to look like this. So there they are, right? Inverses of each other, and you're good to go. You see that reflection. It's nice. All right, now number 2. Before I get into the actual inverse function one, let's first draw this one. Let's make sure we know how to draw it. I want to talk about this one first so you know how to draw the next one after. So we've done transforming cubic functions before. What I'm dealing with right here, this is my h value. My h is 1. That means that my center will be translated 1 unit to the right. So it's this point here. There are some other points on this graph that we would find, such as from here we can go 1, 1, and from here we can go 2, 8. Now 8 is a little off the graph here, but I still want to plot it just to give you the idea of what the curve's actually going to feature, what it's going to look like. And same thing on the other side, -1, -1, and from the center, -2, -8. And again, I'm going to go down here a little bit just to give us the nature of this graph. Because what I want us to expect, or what I want us to do is know how to graph the cubic function after this, and I want you to have an expectation of what its inverse should look like. So, there's a way that you can draw these inverses from the graph without actually calculating its inverse, and of course that's swapping all your x's and y's. I'm not going to do that, so to speak, right here, but what I'm expecting as an inverse is going to be something that instead of going down on y, it's going to go left on x right here in this territory, and then it's going to have a curve up right there, and it's going to split off and cross like that. We're expecting a graph to look like this. This is what the inverse is going to look close to. It's obviously not perfect. There are some points I didn't hit perfectly. But let's go ahead and find its inverse. Let's graph its inverse, and let's see if that's what we get out. So this is y equals x minus 1 quantity cubed. Let's take its inverse. The moment I swap x and y, this x equals y minus 1 quantity cubed. This is the inverse. But how do we graph it? Let's get y by itself and get it in its proper representation there. So to get y by itself, this quantity is being cubed. You are going to have to take the cube root of both sides here. because the cube root of something cubed cancels out that thing, just like the square root of something squared cancels out that thing. So now I'm going to have the cube root of x equals y minus 1. And when I add 1 to both sides, I'm going to get y equals the cube root of x plus 1. Or because this is the inverse of the function, it's going to be written like this. Okay, so there's that final results of that one right there. Now, this is no different as far as transformations go from any other function with regard to behavior. This is something that takes on the form, there can be an a on the outside, there can be an h inside, and a k right here. Plus 1 is your k. So this is a k value of 1, which means we translate our center up 1 unit right here. And a cube root function, guess what? Cube roots are inverses of cubes. So if you imagine that in a cubic function, we go 1, 1, and 2, 8 like here. Now we go 1, 1, and 2, 8. We swap x and y. Instead of going right 1, up 1, right 2, up 8, now we go up 1, right 1, and up 2, right 8. And this one actually runs into my work here, so let me kind of slide this stuff over. So I know that can be a little tricky, especially if you're very new to this stuff. And this is me avoiding using tables. Tables would be really hard for cube roots because you got to pick a value that you can take the cube root of. That's why knowing the behaviors of these functions is really nice and important here. But yes, here's my 1, 1, 2, 8. I just swapped x and y. Instead of right up, I go up right. So now instead of 1, 1, let's go 1, 1 down and left. And now let's go down to left 8 right here. And of course, you know, we are going to get that inverse appearance graph that's going to go through like this and out like that. And hold on, my hand didn't really reach. There we go. So there's that graph right there. And if you turn your head the correct way there, you're going to see that inverse, that reflection, that idea of that thing right there. It's just confirmation of it, graphing a cube root function as well, noting how it's in inverse, and really understand its behavior when you are graphing its inverse, that's what you're doing. You're swapping the y and the x. We swap the y and the x. And that's what we're doing. We're going to do the rest algebraically without graphs. But let me mention this thing on graphs just because I don't think, we're going to talk about it much more here. And don't worry, I'll undo and bring this back. Just because, let me keep the dotted line. Just because we take the inverse of a function does not always necessarily mean that the inverse is a function. So what if we had a parabola? A parabola. Now, we know what functions are, right? For every x, there's only one y. For this x, there's only that y. For this x, there's only that y, etc. Sometimes there are multiple x's for the same y, but there's only one y for each x. If I reflect this across this line right here, then the parabola goes like this. It's a sideways parabola. A sideways parabola is not a function because you have multiple y's for the same x, like this right here. That's not a function. I'm not saying that's okay or that's not okay. I'm just saying that not all inverses of functions are also functions. Specifically true of like even powered functions such as this one right here. So anyway, I just want to make sure, I just wanted to note that. That's just something worth mentioning. The ones that we did were both functions. The inverses were functions as well. And we're good. Excuse me. Okay, let's go down to numbers 3 and 4. Find the inverse of each function. Same thing as before, only now it's an f here, and this time we're not graphing. So I'm going to change f of x to a y, just for my own sake. Let's swap x and y. Once we swap, we're dealing with the inverse. I'm going to go and label that as inverse now. Swap x and y. And listen, the cool thing about inverses, guys, is you're applying inverse operations. What was a plus here, now we got to now subtract, right? Subtract 12 from both sides. Now you see a minus there. And what was multiplication here, 2 times y, is now division. You divide both sides by 2. So you get y equals x minus 12 all over 2. You could do what I did before, like the 1/2 x minus 6. That's totally appropriate because x over 2 is 1/2 x. Negative 12 over 2 is negative 6. But I'm not graphing it, so it's also not a requirement. It's kind of good to know that either one or the other is acceptable. Now, when it comes to writing it in its inverse notation here, we should be writing inverse of f like that. Let me try that again. That's a little unclean. Inverse of f like that. So I'd say that's a good final answer like that, or this one, of course. And that's your inverse, and we're done. I'm not doing anything more to it on that one. Okay, number 4. We still have 3 more of these to do, and just I think they get a little, not necessarily more challenging, just they have different things coming up. But, you know, fractions are a part of the mix. Anytime you're multiplying on one end, there's fractions on the other end. Anytime you're dividing, that means there's going to be multiplication. So let's change that into a y. Let's go ahead and swap, and let's discover its inverse here. So swappage, x and y. And let's get y all by itself. So the last thing that was done here is 5 was divided. So the first thing we're going to do here is we're going to multiply x by 5. So multiply by 5 here, and now we get 5x equals 5 plus y. Those are 5's, not s's. Subtract 5 from both sides, we get y equals 5x minus 5. Or, of course, when I write it in its inverse notation, it'll be inverse. I keep doing that. I'm going to start writing x there by accident. Inverse of, no, you know what I'm going to do is f prime. If you're in a calculus, you know what f prime means. Inverse of your function there is 5x minus 5. And that's the final answer there. Okay, so again, just inverse operations, algebraically switching. I'm sure the graphing was a little more confusing than not, but that helps explain away the inverse stuff. Let me make that in black and white just in case I ever go back to it. And there we go. See that? It's very Rorschach ink blot testy, right? It's got that Rorschachness to it. There you go. Let me thicken those lines as well to match with the first one. There we go. All right, good as new. Okay, here we go. I got 2 more. Calculate the inverses, and then we determine whether these next 4 inverses. So, okay, good on time. All right, number 5 here. Let's swap x and, well, it's, I personally, this is me. I need to write that y to help myself out here. -3 over x plus 1 and then plus 1. So again, swap x and y and then get y by itself. Now you do need to get y by itself, not just to get it in a good graphing form. Whoopsie, I need to put a y there. But also because that's the whole idea. It's the inverse with respect to a brand new x. There's a new x that's represented in the inverse, right? So now to get y by itself here, let's first start with that plus 1. That's kind of the, that's like the loner guy. So let's subtract 1 from both sides. We get x minus 1 equals negative. I'm going to put the -3 on top, right? It's a -3. And then y plus 1 down here. Now, if you want to get y by itself, it also needs to get in its own numerator. So I need to multiply both sides by the quantity y plus 1. Some people aren't really privy at this algebraically. You have to start to get privy with it. Now, it is a quantity. And heck, x plus 1 is also a quantity. I'm not going to attempt to distribute and FOIL this. I'm going to get y by itself in its own right. And there's something I'm going to do with the x minus 1. I don't want it on this side of the equation on the next step here. So let's keep moving forward. That's y plus 1 times x plus, x minus 1, excuse me. X minus 1 equals -3. And now I did handpick these problems. They could have actually gotten a lot harder than this. So it's actually kind of good that we have this. And again, still got to get y by itself. Let's go ahead and divide both sides by that x minus 1 there, right? I don't want to distribute it. I want to kind of get this y by itself. So you could have done something like, I'm really good at knowing that these can kind of just swap places. Multiply both sides by y plus 1, divide both sides by x minus 1. They swap places. You'll see this here in a moment. So we're going to now have y plus 1 equals -3 over x minus 1. See how before x minus 1 was here, now it's down here. Y plus 1 is down here, now it's up there. That's just something that algebraically you do. And then subtract 1 from both sides. So now we get y equals -3 over x minus 1, and then this minus 1 here. So subtract 1 from both sides, there's that. And of course, as that's a g of x, now let's write inverse of g. Boom, like that, and that's your final answer. So there are some things that look very similar. You can tell the only difference in this case was the -1 there. Is that always what happens? No, not necessarily. You saw the other ones have instances in different locations, just this was a rational function and something happens there. And number 6 is going to be very, very similar with regard to what we just did last time. So maybe you can try this one on your own before you hear out what I do. But let's give it a shot. Okay, let's do its inverse. Oh, if you want to give it a shot first, you're going to have to pause this video. But I'm going to keep going. I'm not going to pause and wait for you. Swap the x and the y. It's possible that you could also factor a -1 out of here and create it. It can look a lot like this last problem. It can look like almost no difference if you really know the algebra behind that. But I don't want to confuzzle you more if you're going to practice something that, I don't know. But you can factor out a -1, and the negative can look just like that. Anyway, so right here, I want to subtract 2 from both sides. I get x minus 2 equals 4 over -y minus 3. If you trust me, I did just mention that in this scenario, if I multiply both sides by -y minus 3 and divide both sides by x minus 2, effectively, they do swap places. They do swap places here. So I will have a -y minus 3 equals 4 over x minus 2. There's just the math on that one. You don't always just swap places on things. It was the fact of the matter of the math that was going on by multiplication of one and division of the other. Add 3 to both sides, and I have negative y equals 4 over x minus 2, and then plus 3. And then I got to, multiply both sides, divide both sides by negative 1 here. Basically, what's going to happen is each term is going to get a sign change. So this turns into a y. This 4 turns into a negative 4. Don't change the sign on the bottom as well. I mean, you can do it to the whole fraction, right? I can put just a negative just next to the fraction itself, just represent it as one thing. But don't change the x minus 2. You just apply it once. If I do it on top and bottom, that's negative 1 over negative 1. That turns into a 1. That doesn't do anything. And then a minus 3 right there. And then y becomes, what was this? This was a g. So this becomes inverse of it. All right, there it is. And, we're not graphing rational functions. I purposefully made sure that we weren't going to graph any. We're saving rationals for my own class and stuff for a future unit. But yeah, you can see this was very similar in the end because really there was a negative 1 that was kind of, placed inside of there. Here were some other ones. I was going to say, I meant to do more cubes and cube root ones like this one that you saw right here. But yeah, if you have something squared, you take the square root. Cubed, you take the cube root, things like that. That's going to occur to cancel those out. Every kind of thing in here has an inverse, and that's what we're going to be playing with. All right, the last 4 problems that we have here, guys, it says state if the given functions are inverses. Now, it's what they are asking you to do is see if g of x is the inverse of f, or if f of x is the inverse of g. Obviously, if one's the function of the other, then the inverse of the other, then it works, right? We're testing to see that. So you could do exactly what we did before. You could swap x and y and see if one becomes the equation of the other. But there's a different test that they kind of want you to apply, and it's using what's called a composition of functions, which means you apply a function of another function, or of itself, but you apply a function of a function. So instead of a function of a variable, you take a function of a function, like instead of f of x, let's do f of g of x. That's a composition of functions, or g of f of x. And if you apply a function to its inverse, what's going to happen in those instances? Because I shouldn't have undone the other thing here. If g of x is truly the inverse of f, then when we do f of g of x, what we're testing to see is if it's f of inverse of f. And if it is the inverse of f, the result is going to be just x. What you're going to get out for the inverse of f, because remember, when you take f of x, you get y. When you take f of the inverse, f of y, you should get x. Or the thing that's acting like a y for the other thing, right? Because the x's and y's swapped. So that's what we were trying to get out of here. And same with g. When we take g of f of x, that means that, or what we're hoping is that we're taking g of its inverse, which then the result should be x as well. That might sound a little confusing to you, and sometimes the math here can get a little overbearing. So here's what we're trying to see. Now, when I say g of x and f of x, I mean the expression that we plug into here. Okay, so here's what we're going to do. Let's try number 7. I'm going to attempt to take the f of g of x, which means I'm taking the f of, what's g of x? This thing. Negative 1/2 x minus 1. And what that really means is, in this expression, negative 2x minus 2, instead of writing an x, I'm going to write this. Whatever is the input takes x's place. If this said f of booger, booger would take x's place. So negative 1/2 x minus 1 is going to take x's place in the function f right here. Negative 2 times negative 1/2 x minus 1, and then minus 2 like that. What we're going to do is we're going to attempt to simplify this expression, and if the expression simplifies to just x, then that means it is the inverse. That means g of x is the inverse of f. So let's distribute negative 2 times negative 1/2 x. That is positive 1x right there. And then negative 2 times negative 1 is positive 2, right? That's the distribution. And then we have this minus 2 right here. And 2 minus 2 is 0, so you're just left with x. So yeah, this just turned into x. That means that these are inverses of each other. That is a big fat yes. Yes, these are inverses of each other. That's good. Now, if you want, I'm not going to do this for every other problem. I'm just doing it for this one to show you that it works. I could have done the same thing with g of f of x right here. G of f of x means I would be taking g of f of x's expression as negative 2x minus 2. And what we're going to do is we're going to substitute negative 2x minus 2 in for x right here. And then we're going to see if we get x as a result. So negative 1/2 times the quantity negative 2x minus 2 minus 1. A lot of negatives. Let's distribute a negative 1/2 into these two things right here. Negative times a negative is a positive. So half of 2x is 1x, so just x. And half of 2, negative times negative is positive. Half of 2 is 1, so x plus 1. And then minus 1 plus 1 minus 1 is just x. So once again, we just get an x again. So once again, yes. You only need to test it once. I think we can trust the math on one of them. You don't need to do both. You're good. So yes, these are inverses of one another. And of course, if we swap the x's and y's and we got one by itself, this is what the equivalent would be on the other side. Okay, let's go ahead and let's try number 8 now. Let's take, this is with the letter n. Let's try g of f of n. And sometimes it's easier. Sometimes you want to look carefully at which version you're going to plug one into, because sometimes it's easier to do one versus the other. It's hard to explain. Depends on whether you have to expand like a huge polynomial. I think these ones are probably fine either way. Let's just go ahead. Let's try g of f of n. I don't know if that's the smart version or not. Depends on if you want more or less fractions sometimes. I'm just jumping into it. So we are doing g of 2 plus 1/2 n, okay? So that means that 2 plus 1/2 n is going to take n's place right here. 2 times, instead of n, we're going to write 2 plus 1/2 n, because that is f of n, and then plus 5. Let's see if we just get n out. Let's see if the result is just n, because n is our independent variable now. 2 times 2 is 4. 2 times 1/2 n is n, so we get 4 plus n, and then plus 5. That becomes n plus 9. So that's not just n. That's not just n. Because it's not just n, that means that these are not inverses of each other. Automatically, if one's not the inverse of the other, when we apply the composition, we don't just get n out, then the other way shouldn't work either. This is a no. This is a no. We don't have to test more than that. We didn't just get n out. All right, let's try number 9 here. And yeah, I don't know if there's a preferred version, one or the other, so I'll just go straight into it. Let's try g of f of x. G of f of x there, that's going to be g of 8 minus 7x over 2. This is going to go ahead and take the place of x in the g of x equation. So negative 2 times, fraction within a fraction, 8 minus 7x over 2 plus 8 all over 7. That's a lot to work with. Actually, not really. Check this out. Instead of distributing right here, you have negative 2 divided by 2. That is negative 1. So there's still a negative outside of there, but now there's no more fraction here. So now I just got to distribute the negative into the 8 and the negative 7x. So that's going to give me negative 8 plus 7x. And then there's this plus 8 right here, and this is all divided by 7. All right, well, negative 8 plus 8, that's 0. And you're left with 7x over 7. And 7 divided by 7 is 1. So you are left with x. And that's what we're looking for. We got this down to x. Yes, these are inverses of each other here, because the g of f of x was x. And of course, if I did f of g of x, I should be getting x back out. Same kind of deal. Those are inverses. Awesome. Last one, number 10. And these are the ones that could get, all depending on which way you plug it in, could get a little weird. I'll show you both versions just so you know how cubes and cube roots work with each other, canceling things out and stuff. And let me move my face to fill it out. This is the last problem, running into the half-hour mark. Here we go. Number 10, f of n equals n cubed plus 1. G of n equals cube root of n minus 1. If I take the f of g of n, I'm hoping to just get n back out, which means we're taking the f of cube root of n minus 1. Okay, that's going to be, this is cube root of n minus 1 is going to go in for n. So the cube root of n minus 1 quantity cubed and then plus 1. Well, the cube root of something cubed is just means you just get this guy back out right here, just that n minus 1. So that becomes n minus 1 and then plus 1. Negative 1 plus 1, of course, is 0, and you're just left with n. All right, we already know that this is a yes scenario. That's awesome. Yes, these are inverses of each other. But let's try the other side just to kind of, again, familiarize ourselves with the cubes and cube roots and canceling each other out. So let's do this one more time. Let's do the g of f of n, which is g of, what's f of n? N cubed plus 1. And that's going to go ahead and take place of n inside g's function right here. So that's going to be the cube root of, so instead of n, I'm going to write n cubed plus 1. And then there's also a minus 1 inside there, right? N cubed plus 1 minus 1. Now, these didn't really need parentheses. That was just for substitution. It's not like I'm distributing anything. There is a 1 minus 1 there. That's going to be 0, right? So that becomes the cube root. So those are gone. So that becomes the cube root of just n cubed. You know what the cube root of n cubed is? Just n. Just n. All that cancels out there. So that's a yes. That's a yes. That one works as well. And yeah, you know, sometimes they're weirder. Sometimes they're, you know, easier, harder, all depending on what they are. But you saw an example of a no. Sometimes the no's can get really extreme because they're just not really related. You can get big things with fractions and fractions within fractions. And, you know, I tried to choose some things that were reasonable, and I'd say that these ones were. But yeah, so that's what we're working with, guys. Swapping the x's and the y's and applying a composition of functions to make sure that they work out with that symmetry that we're looking for. You can see the symmetry right here as we reflect across. That ought to do it for this one, guys, with inverses of functions. This is Mr. Robinson. Thank you so much for tuning into this one, and I will see you in the next one.